Hello dear student, welcome to the course of Electric Machine 1, the new lecture. Today we are going to study the rotational reversal of a machine or a DC motor, then starting a shunt motor, also the stopping of a shunt motor in dynamic braking. So how we can rotate or reverse the direction of a DC motor. To reverse the direction of rotation of a DC motor, we must reverse either the armature connection, the connection in the way we connect the armature just by reverse its connection. The other thing is the shunt and series field connection, both the shunt and series field connection. When we can reverse these two, we got the reverse the direction of rotation of a DC motor. Now starting a shunt motor, how we can start a shunt motor? If we apply a full voltage to a stationary shunt motor, the starting current in the armature will be very high, and we run the risk of it means that if we directly apply the full voltage to a stationary shunt motor, that is the starting current in the armature will be very high, and the following risk is possible or will occur. First one is burning out the armature. The second one is the damaging the commutator and brushes due to heavy sparking. The third one is the overloading the feeder, the one in which this motor is connected, and the fourth one is breaking off the shaft due to mechanical shocks, and the fifth one is damaging the driven equipment because of the sudden mechanical hammer blow. So this is the possible risk if we directly apply a full load voltage to a stationary shunt motor. So all DC motor must therefore be provided with a mean to limit the starting current to a reasonable values in order to overcome the previous we explained that how to minimize or overcome these losses. All DC motor need to provide a mean to limit the starting current to a safe value, usually between 1.5 and twice the full load current. So one solution is to connect a rheostat in series with the armature. The resistance is gradually reduced as the motor accelerates and is eventually eliminated entirely when the machine has attained full speed. So initially a high resistance, then with the gaining the speed or acceleration, the resistance will be decreased and eliminate entirely when the machine has attained the full speed. In this way we can overcome or reduce the starting current to a reasonable value. But nowadays electronic methods are often used to limit the starting current and to provide the speed control. So this is the method, or in this way we can start a shunt motor by connecting a rheostat in series with the armature. Now how to stop a motor? Mostly people believe that stopping a DC motor is a simple operation. Unfortunately, this is not always true. When a large DC motor is coupled to a heavy inertial load, it may take an hour or more for the system to come to a halt. So for many reasons, such a lengthy deceleration time is often unacceptable, and under these circumstances we must apply a braking torque to ensure a rapid stop. One way to brake the motor is by simple mechanical friction. In the same way we stop a car. A more elegant method consists of circulating a reverse current in the armature so as to brake the motor electrically. Two methods are employed to create such an electromechanical brake. The first one is dynamic braking and the second one is plugging. So we will study first the dynamic braking. Dynamic braking. We want to brake the motor by circulating a reverse current in the armature. So this is one of the methods for it. Dynamic braking. Consider a shunt motor whose field is directly connected to a source ES and whose armature is connected to the same source by means of a double through switch. The switch connects the armature to either the line or to an external resistor R. So for this dynamic braking, for understanding purposes, we consider a shunt motor whose field is directly connected to a source of ES and the armature is also connected to the same source by means of a double throw switch, and the switch connected the armature to either the line or to an external resistance. When the motor is running normally, and that is in normal condition, the direction of the armature current I1 and the polarity of the counter EMF E0 are shown in figure. This is the diagram for we have a supply S in which we have a field winding and armature winding. We can connect it with the external resistance or directly through a line, and we have the counter EMF direction and I1 direction. This is the field current direction. So in this situation, that is motor running normally, we neglect the armature IR drop. So in this way, E0, that is the counter EMF, is equal to the supply or the source. Next, if we suddenly open the switch, the motor continue to turn, but its speed will gradually drop due to friction and windage losses. On the other hand, because the shunt field is still excited, indeed voltage, that is the counter EMF, continue to exist, falling at the same rate as the speed. The motor is now a generator whose armature is an open circuit. Now if we suddenly open the switch, that is this one, so the field is still excited and its work as a generator having an open armature. So this is what it looked like. This is the open switch. This is the first figure, this is the second, and we will study the third one. Let us close the switch on the second set of contacts so that the armature is suddenly connected to external resistance. Voltage, that is the counter EMF, will immediately produce an armature current I2. This is the case when we connect the armature, this one, with the external resistance. Sorry. So a current I2 flow because of this counter EMF. However, this current flow in the opposite direction to the original current I1. That's what we want, that we need to flow the current that is in opposite in direction with the main current, so it flow that a reverse torque is developed whose magnitude depend upon I2. So due to I2 we get a reverse torque and whose magnitude depend upon I2. The reverse torque bring the machine to a rapid but a very smooth stop. In this way the reverse torque opposes the main torque and the machine to stop but with there is a smooth stop. In practice, the resistors R is chosen so that the initial braking current is about twice the rated motor current. The initial braking torque is then twice the normal torque of the motor. So because of this resistance, the current I2 flow, and we need to choose this resistance so that the initial braking current is about twice the rated motor current. So the initial braking torque is then twice the normal torque of the motor. So as the motor slows down, the gradual decrease in E0 produce a corresponding decrease in I2. Consequently, the braking torque becomes smaller and smaller, finally becomes zero when the armature ceases to turn. The speed drops quickly at first and then more slowly as the armature comes to a halt. The speed decreases exponentially, somewhat like the voltage across a discharging capacitor. So in this method, that is the dynamic braking method, we just need to circulate a reverse current in the armature. So this reverse current, we connect armature with an external resistance. This is the first case when we connect both field and armature with the source. Then we disconnect this armature and we connect it with the resistance, and this way I2, the current flow that is in opposite direction to the main current, and it produced torque that is opposite to the main torque. In this way the motor stop. So this is the dynamic braking method. Thank you.